Hello. In today's topic, we look at something's called factorials, permutations, and combinations. Essentially what we're doing is we're looking at all the unique ways that we can count things. The reason that we're looking at that is because we're studying probability, and probability at its heart is concerned with the number of total successes, so number of ways that we can count to make successes, divided by the number of total possible outcomes. We have to be able to count successes and total possible outcomes. So we're looking at the variety of ways that you can count items. To begin with a simple example to kind of guide you with your intuition, imagine that you have 3 books sitting on a shelf. One has a green spine, one's blue, one's red. I want you to ask yourself, how many unique ways can I rearrange those books on the shelf? So I could have green, blue, red, or maybe I could do green, red, blue, and we would say that those are unique because the order has changed. So take a second, maybe try it for yourself. Otherwise, I'm going to continue. So you can pause the video if you want to see how you did. But if you think about it, there are going to be 6 ways that I can rearrange those books. Each arrangement where order is important is called a permutation. So a permutation is a specific arrangement where order is important. So I could have green, blue, red, or like I did a second ago, I can rearrange the red and the blue to make green, red, blue. So essentially there's 2 different permutations for every single situation where each color leads off. So I could have blue, green, red, red, green, red, blue, green, or red, green, blue. So we'd say that there's 6 different unique ways. There are 6 permutations. But thinking about this in your head is kind of an inefficient method. Instead of doing that, I could actually use the counting principle. I could ask myself, simply how many options do I have for the far left book? So if I was going to rearrange them, well, there are 3 options to start off, because I haven't chosen it yet. So the first far left option has 3. But once that one has been set, let's say it's green, now there's only 2 options for the middle. The middle can either be blue or red. Let's say I say that the middle is blue. And now there's only 1 option for the far right, and that's red. Well, 3 times 2 times 1 is going to lead me with 6. That's the counting principle that we've used before. But this idea of unique arrangements for n items gets used so often, we have a special name for it. It's called the factorial. So in our case, 3 with an exclamation mark is how we write it mathematically. It's read as 3 factorial. And it simply means 3 times 2 times 1. You start at the number, and then you multiply by the integers less than it all the way down to 1. So 3 times 2 times 1 leaves me with 6. As I hinted at, we call this a factorial. A factorial of a positive integer n product meaning multiplication. It's the multiplication of all of the positive integers less than or equal to n all the way down to 1. And we define 0 factorial to be 1. I'll give a few justifications for that here in a second. But just for example, let's say you start with 8 factorial. 8 factorial would equal 8 times 8 minus 1 is 7, times 8 minus 2 is 6, all the way down until I multiply by 1. That's what 8 factorial would mean. The factorial actually tells you the number of ways you can arrange n unique items in a line. So imagine I had 1 item. How many ways could I rearrange it? Well, just 1 way, because there's just 1 thing in the line. 1 factorial is equal to 1. Once I've reached 1, I stop. 7 factorial. How many ways could I rearrange 7? If I had 7 people in the line, how many ways could I rearrange them? And each arrangement would be different because the order is different. 7 options for the first person, then 6 for the second, then 5, then 4, then 3, then 2, then 1. Type that in your calculator, you're going to end up getting 5,040. 0 factorial, we said was defined to be 1 in the definition for this vocab word. You could also think about it, if I have 0 items, how many ways could I rearrange them? Well, just 1 way, because there are none of them. I just don't rearrange them. So there's kind of a philosophical reason why 0 factorial might be 1. Here's another pattern that might enable you to understand why 0 factorial might be 1. So 5 factorial, 5 times 4 times 3 times 2 times 1 is 120. 4 factorial is 24. 3 factorial we saw was 6. 2 factorial is 2. 1 factorial is 1. There's actually a pattern going on as I go down here. So 120 to 24, it's actually divided by 5, because the only difference between 5 factorial and 4 factorial is 5 factorial is multiplied by 5. So I divide by 5. 24 to 6 is a divide by 4. 6 divided by 2 is divide by 3, because the only difference between 3 factorial and 2 factorial is 3 factorial has a multiply by 3. Now I divide by 2, and the last one would be divide by 1. And if I take 1 and divide it by 1, I get to 1. So there's actually kind of a pattern why 0 factorial might be 1 as well. Last one, then I'll show you you can actually use your calculator to calculate some of these. 6 factorial divided by 4 factorial. Well, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And 4 factorial is 4 times 3 times 2 times 1. Hey, 4 divided by 4 is 1. 3 divided by 3 is 1. 2 divided by 2 is 1. 1 divided by 1 is 1. So I did times 5. Well, that's equal to 30. So what you've actually kind of seen is 6 factorial inherently has 4 factorial in it. Because if you look right here, this is 4 factorial, and so is this. So that's why they would divide each other out. So I'm just the 6 times 5. You can use your calculator to calculate these. You're going to first, you have to type the number that you're going to take the factorial of. So let's do the 7. So what you do is you're going to hit 7, then you'd hit math, you tab over to probability, then you choose option 4, the factorial. And this is for a TI-83 or TI-84. So 7, then I hit the math button, I tab over to probability, and I choose option 4, the factorial. And I hit enter, and there's my 5040. So we can use the calculator to calculate factorials as well. Now we're going to try a few examples of where's this idea of factorials and unique arrangements gets used. So let's say a student tells his friend the password for his phone uses the numbers 5, 3, 2, and 1. How many different passwords are possible? Well, all this is how many ways can I uniquely arrange the numbers 5, 3, 2, and 1? Well, there are 4 items, so I would do 4 factorial. There's 4 ways to choose the first number, either a 5, a 3, a 2, or a 1, then 3 for the second, then 2 for the third, and then once the first 3 have been chosen, there's only one option for the last. 4 times 3 is 12, times 2 leaves me at 24. 4 factorial, so there are 24 different passwords possible once I know the numbers. Second situation, let's say a travel agency offers an Italian package for visits to 5 cities. The customer can pick the order of the cities. How many different packages are possible? Well, 5 different cities. How many ways can I rearrange 5 cities? 5 factorial. Well, 5 factorial is really just 5 times 4 times 3 times 2 times 1. Well, that's just 4 factorial. And we just found 4 factorial up above was 24. So this is really just going to be 5 times 24, which is 120. Or if you want to, you can grab the calculator, type in 5 factorial, or 5 times 4 times 3 times 2 times 1. I'm just being a little bit more efficient. That's how I rearrange them if all of the items are unique. So that's what a factorial was, if all of the items are unique. But what if all of the items are not unique? What if there's some repetition? So we're going to extend our book idea. Imagine I've got more than 3 books on the shelf. I've got 11 books on the shelf. However, there are some repetitions. Like I see there are 3 green books, there are 4 blue books, and there are 4 red books. How many different ways could I rearrange them in such a way that each arrangement is unique? Well, you'll see because there's some repetitions, I might say from the beginning, well, there are 11 factorial ways to rearrange the 11 items, because there's 11 items, 11 for the first spot, then 10 all the way down to 9, 8 to 1. So the number of ways to rearrange all the items is 11 factorial. But I'm really overcounting some of these. So some of these I'm thinking are unique, but they're really not. Like, for example, if I change this first green and this last green, and I switch their spots, would you say that arrangement is any different? No, you'd still say it's green, blue, red, green, blue, red, green, blue, red, blue, red. Same arrangement. So I've overcounted some of these. Well, how many ways have I overcounted the greens? Well, that's really how many ways could I rearrange these 3 greens. There are 3 greens, so there are 3 factorial ways to rearrange the greens. 3 factorial 6. So I've overcounted by 6. So I need to divide my total by 6 for the greens, but I have some repetition in the blues. There's 1, 2, 3, 4 blues. So there are 4 factorial ways to rearrange the blues in such a way that I couldn't identify the arrangement as being different from one another. And there's 1, 2, 3, 4 reds. So I need to divide by 4 factorial for the reds as well. And that will then tell me how many unique ways there are to rearrange all of them. So I need to take the total number of ways to rearrange all of the items and divide out the number of ways to rearrange the identical items, because I've overcounted those because they aren't uniquely different than the prior ones. So grab a calculator maybe. And I'm going to type in, so 11 factorial divided by, now this was what, 3 factorial times 4 times 4 factorial. Well, 3 factorial is easy. 3 factorial is 6. 3 times 2 times 1. Times 4 factorial is 4 times 3 times 2 times 1. We've done that. That's 24. Times another 24. And I end up with 11,550. So 11,550 ways to rearrange those 11 books where I have some repeats in there. You can imagine where this might get used in like a medical field. It looks very similar like a DNA sequencing. So if you're, counting the number of ways to have unique DNA sequencing, this would be the fundamental mathematical principle. Going to give you a chance to try. So first scenario, how many different batting orders can be formed for a 9-person baseball team? Second situation, a building contractor is planning to develop a subdivision consisting of 6 one-story houses, 4 two-story houses, and 2 split-level houses. And how many unique ways can you rearrange the 12 houses? The second one is very similar to the one we just did with the books where there's some repetition. Instead of saying 6 reds, 4 blues, 2 greens, it's 6 one-story houses, 4 two-story houses, and 2 split levels. So pause it, give yourself a chance to try, see how you did, and then come back and check in. Okay, scenario number 1 is just how many ways can I rearrange the 9 people in the batting order? That's just 9 factorial, so 362,880. Situation number 2, there are 12 houses, so 12 factorial is the number up top, but I need to divide by all of the repeat orders. There's 6 factorial ways to rearrange the 1-story houses, 4 factorial ways to rearrange the 2-story houses, and 2 factorial ways to rearrange the split level houses. So I need to divide it by 6 factorial times 4 factorial times 2 factorial, and that's going to be 13,860. That's as far as I can go once I've used all of the possibilities. But what if I am not able to choose, all of them? So we're going to go back to the Italian vacation package where they offered 5 cities. But let's say instead of saying that you could visit all 5 of the cities, you only had to choose 3 of them. How many different packages would be available now? For option number 1, there's still 5 cities. For option number 2, there are 4 cities. And for option number 3, there are 3 cities. But I need to stop there because now I visited 3 cities. So 5 times 4 times 3. 5 times 4 is 20 times 3 is 60. So there's only 60 possibilities now if I'm going to visit 3 cities. Note, you could have also written the above using factorials. 5 factorial divided by 2 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1, and you'll see 2 divided by 2 is 1, 1 divided by 1 is 1, and that's going to leave me with 5 times 4 times 3 times 2, or 5 times 4 times 3. Essentially, it's saying I need to stop 2 short because I'm only able to pick 3. So I'm not able to pick the last 2, so I need to divide those out. This special property, we have a name for in mathematics. It's called the permutation formula. So the number of permutations of n objects, if I want to select r of them, is going to be the division of n factorial divided by n minus r factorial. Essentially, it's this. I need to take how many unique ways there were for all of the items and divide out the ones that I'm not able to select. So in our case a second ago with, what was it, permutation of 5, and I need to select 3. That would be 5 factorial divided by 5 minus 3 factorial, which is 5 factorial divided by 2 factorial. I'm not able to choose the last 2, so I need to divide them out, which is going to mean I use 5 times 4 times 3, and that was my 60. There's a built-in function in the calculator that allows you to calculate these, but you first need to hit the number of objects that you're selecting. Then you hit Math, tab over to Probability, and select Option 2, NPR. So let's do it. 5. Then I go to Math, tab over to the Probability, select Option 2, and PR. It's a permutation because order's mattering. And then I said I wanted to select 3 cities from the 5. And there's 60 ways to select 3 cities from the 5 total possible. We're going to try it one more time using the formula and then the calculator. So if I wanted to select 3 items from 6 where order is going to matter, let's first say n is equal to 6. I need to select 3, so r is equal to 3. So we would say permutation 6 selecting 3 is going to be 6 factorial divided by 6 minus 3 factorial, which is 6 factorial divided by 3 factorial. I need to stop 3 short because I'm not able to pick the last 3, which is going to be 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1. Divide these out, and I'm just going to end up with 6 times 5 times 4. 6 times 5, 30 times 4 is 120. So 120 permutations if I'm going to select 3 items from 6 total. If I use the calculator, I would choose, so hit 6, go over to Math, select Probability, NPR, selecting 3, 120. Same thing. Here's an example where that might be used. So let's say a soccer team has 11 players. How many ways can a coach select the order of 5 players to take penalty kicks for a tied game? So we're going to first kind of use the equation idea, and then we're going to use a calculator. So if he's selecting 5, really what it means is that there's 11 options for the first taker times 10 options for the second taker times 9 times 8 times 7. Well, that is simply our formula. Permutation 11, 5 is really 11 factorial divided by 11 minus 5 factorial, which is 11 factorial divided by 6 factorial, which means I need to not choose the last 6. I need to divide them out, which is going to leave me with 11 times 10 times 9 times 8 times 7. If you grab a calculator, it would end up being 11 times 10 times 9 times 8 times 7. You end up with 55,440 different ways to select the 5 kickers. Or you grab a calculator and you do permute 5 from 11. So 11, math over to probability, select option 2 and 5, and there's the 55,440. So same answer. And that's what we call a permutation. Last kind of topic that we'll consider is like, what if in the prior situation the coach didn't care about the order of the kickers, but rather just which 5 were chosen? So let's say that Jake, Kevin, Luke, Paul, and George were selected. Well, if the order doesn't matter, then that's the same as Kevin, Paul, George, Jake, and Luke. So therefore, our prior total is too big. We need to divide out our prior total by 5 factorial, because that means there's 5 ways to rearrange the 5 kickers. And because I considered them unique before, I've overcounted them. So if I look at the definition in the book or where the equation comes from, it says this. It says the number of combinations of n objects taken r at a time is the quotient of n factorial and n minus r factorial times r factorial. That's kind of a mouthful. Let's just break it down to pieces. It looks like this, but we already have a portion of this from before. So I'm going to zoom in a little bit. This piece right here, n factorial divided by n minus r factorial, that is just the permutation. That is PNR. That's how many ways could I have selected r from n. And the last bit I need to do for the combination is divide by r factorial, because that's how many ways I could uniquely arrange those r items once they were selected. So there's kind of really a shortcut formula. It's really saying the combination is equal to the permutation divided by r factorial. Once I've selected all of the items, I need to divide by how many ways I could have rearranged those items, because since order is no longer important, I have overcounted. So if I go back and calculate the number of ways he could have chosen the 5 kickers, in this case, since order does not matter, it's a combination, the formula would be this. We would do the 5, the 11 factorial, divided by 11 minus 5 factorial times 5 factorial. Factorial over 6. See, these numbers down below always have to add up to the total. The 6 is how many things were not selected, so where I need to stop. That was the permutation. So this right here is really just 11 permute 5, and then I need to divide it now by the 5 factorial. Because once I've selected the 5 kickers, I need to divide by 5 factorial, because there's 5 ways to rearrange them that I've counted them as different, but they are no longer different. Grabbing this, so 11 permute 5 divided by 5 factorial. Well, 11 permute 5 is just going to be 11 times 10 times 9 times 8 times 7 divided by 5 factorial. Because once I've chosen these, I need to divide by 5 factorial, but we did that just a second ago. 11 times 10 times 9 times 8 times 7, that's 55,000. What was it? 440. So this is really just 55,000. And I need to divide it by 5 factorial, because there's 5 factorial ways to rearrange all those items. If you type that in a calculator, divide by 5 factorial, you're going to end up with 462. You'll see it's a lot less. It's a lot less because since order is no longer important, there's not as many unique arrangements. You'll see also in the formula up here that the combination is always going to be less than the number of permutations because you have to divide by r factorial. You don't have to do this calculation every time. I just wanted to show where it came from. You can just use a calculator. So in the calculator, really what you have to type in is 11 first, 11, and then you're going to go to math, over to probability, select option 3 now since it's a combination, choosing 5. So 11, choose 5, 462. Same number that we had when we used the formula. So that's what we call a combination. So the difference between a combination and a permutation, combination order does not matter, and with a permutation, order matters. A permutation is always going to have more than the combinations because if order matters, there's more unique ways. So for each of these situations, we're going to state whether it's a combination or a permutation and then calculate. So let's say the state plans to develop a new section of highway. They receive 16 bids and they're going to select 4. How many different selections are possible? Well, since order doesn't matter, just being selected matters, it's going to be a combination. So order doesn't matter, it's going to be a combination. So we need to do, what was it, 16, choose 4. Grab my calculator, 16, choose 4. There's 1,820 different selections of the 4 that could occur. A computer program asks you to make a 7-character long password using numbers and letters, but no character can repeat. How many different passwords are possible? Order definitely matters for a password. Since order matters, this is going to be a permutation. We first need to know how many things we're choosing from or selecting from. Well, we're using numbers, so 0 to 9 means 10 numbers. How many lowercase letters are there? There's 26, so that means there are 36 possible. So I need to select 7 from 36 with order mattering. It's going to be large. There are a large number of passwords possible. 36 permute 7. 4.21 times 10 to the 10th. That's 42 billion different passwords are going to be possible. So once order starts to matter, the number of unique arrangements really starts to go up. All of this is kind of synthesized in your book on page 172 if you need it. The fundamental counting principle, how many ways can I select m things for the first and then n for the second? Well, it's m times n. For permutations, when order starts to matter, how many ways can I uniquely arrange n items? That's n factorial. How many ways can I select r from n items where order is going to matter? That's a permutation. How many ways can I rearrange n items if there are some repeats? So I need to divide out how many there are of each of the repeats. That was like the book one or the contractor building the different houses. And the permutation is when order no longer matters. So I need to essentially take my permutation equation and divide by r factorial. So all of this is synthesized on page 172 if you want a little summary. Going to give you one last chance to try. State whether each is a combination or permutation, and then calculate the number of possible arrangements. So pause the video now and come back and see how you did. Situation number 1 is a permutation. If there are 8 skiers competing in a race, how many different ways can the top 3 finish? So order matters. That there's definitely a difference between first and third. That would be a permutation. So we would say there's 8 permute 3, 56. From the senior class of 300, how many ways can we select 3 people for student council? Well, just being selected is important. There is no order here. So it's a combination. 300, choose 3. It would be 4,455,100. And that completes today. Thank you very much and have a good day.